Log on, tune in, find out. Another good idea from Cambridge.
Yaroslav Kurylev as a speaker. He's professor at UCL, has done a lot of work on spectral inverse problems and inverse problems in general, and will talk today about stability for anisotropic problems. And yes, we are looking forward to
Thank you very
hear
much.
from you.
First of all, I think I understand what this lecture takes place over the sun. Now, the second thing, I apologize for those who were at my talks in Madrid less than 1 month ago, because this is actually a very squeezed version of what I was telling them for, I think, 6 hours or something. And the third thing.
Did you switch on your...
Right. I think I have a strong voice. The third thing is that although I agree with Rainer Kress that it's better to have at least one proof, there will be no proofs. There, however, will be a couple of definitions that probably will be new for you. Okay? Now, already in two lecture courses of Günther and Liliana, you come across, when you deal with the wave equation, you come across geometry. You come across Riemann metric, and you come across the distance and geodesics. So let me recall you that at Günther's talk and at Liliana's talk, you had a velocity of the wave propagation in some domain, omega, and this velocity of wave propagation, c of x, it gives rise to the underlying metric. So we have the point x and point x plus dx, and this in Rn. Then the elementary distance between x and d and x plus dx will be the following one. dl squared between x and x plus dx was c minus 2 of x, the length of this elementary vector dx squared. So that was, so the metric on our domain omega has a length element associated with velocity of the wave propagation. And in this case, that was considered in the previous lecture courses, the corresponding metric was isotropic. It really didn't matter in which direction you go. As soon as you go the same absolute value of dx, the elementary length will be the same. So all directions in the space are different, although the velocity depends upon point x. However, in many real-world materials, the velocity of wave propagation will highly depend upon direction. For example, in our muscles or in crystals, velocity will be different if you go to different direction. So geometrically, one of the ways to describe it is to introduce anisotropic metric. In this case, when you go from x to x plus dx, and dx is a vector, so it is dx1, I put here m, dxm, then the elementary length element will be sum ij from 1 to m, gij of x, dxi, dxj. Okay, and here, by the way, I think in geophysics called slowness, gij. So here gij is a symmetric matrix function that has the following property. It's positive definite. Now, from now on, I drop this sum. So when you have upper and lower indices, the same, you take the sum from 1 to m. That's Einstein's summation. Yes, absolutely. So this more than some constant. Thank you very much. C0 by the length of size 0, and this is for all x belonging to the closure of M. So that is the condition. And in this lecture course, well, not course, sorry, it was course in Madrid. Here's just a talk. Gij of x is C infinity. Okay. So in this case, you have a Riemannian structure on your domain omega, and because you have an elementary length, when you go from the point x to the point x plus dx, you can evaluate the length of any curve from x to y. So if it is curve gamma, you can find the length of gamma, and so length of gamma. And so if gamma is gamma of t, it will be integral from 0 to 1. So at time t equals to 0 we are at x, at time t equals to 1 we are at y, and here stands gij x dot I of t, x dot j of t dt. So this will be the length of this curve in this metric. And then the distance between x and y will be the infimum of the length of all curves gamma that connects x and y. Okay, that will be the distance between points x and y. So you go along all routes from x to y and then choose the shortest one. If you remember, when you have a velocity c in the lectures of Liliana or Günther, then the associated differential expression was so you have c of x, and you go to differential expression c minus 2 of x Laplacian of x. Right? That was appeared in the wave equation. So what will be the analog? Well, not direct analog, because this is not really a Laplace-Beltrami operator, except for two-dimensional case. But still, what will be the analog of this differential expression when you have an isotropic medium like that? Then the analog of this expression will be Laplace-Beltrami operator, or Laplace-Beltrami differential expression. And what will be that? I'll denote it by delta G. So G, because it's due to this matrix Gij, and delta G of f will be G minus 1/2 di Gij G 1/2 djf. Now what is what here? Please recall that when we have lower and upper indices, this means we take the sum, I from 1 to m and j from 1 to m. Okay? So now here Gij, as is Günther's talks, was Gij minus 1, inverse matrix to this matrix tensor Gij, and G is the square of the determinant of this matrix Gij. Okay. This scalar G is determinant of the matrix tensor Gij. So this is Laplace-Beltrami, I put it differential expression on our omega. Now, similar to the fact that for c-squared Laplacian we can associate wave equation, but also just various operators, elliptic operators, we can associate with this expression different operators. The first one is, for example, Laplace operator with Neumann boundary condition. So it is Neumann boundary condition. So the domain of this operator is the function h2 of m of omega with the following condition, that if you look, that is a normal. That's a unit normal outside unit normal to n. So the condition will be the following, that Gij ni dj of u on the boundary equals to 0. So we can look, and then This is the domain operator, and the operator acts as following. It's just acts as f. So it is delta G of u. So that is one object. That is the Laplace-Beltrami operator with Neumann boundary condition. And what we can say about this Laplace-Beltrami operator? As you already understand from Andreas' talks, that when operator says self-adjoint, we are lucky. And actually, this operator is self-adjoint. The only point you should take care about in which space it's self-adjoint. It turns out that the volume that associated with this Laplace-Beltrami operator, or better say with this metric, is the following volume element. This is square root of g, the determinant dx1 dxm. Okay? The volume that is associated with the Riemannian metric is this one. Actually, I will also use normalized volume, or probabilistic volume, which I denote by d mu g. And this is just this Riemannian volume divided by the volume of the whole domain. Then d mu g, the total measure, will be 1. That's why it's called probabilistic volume. Then it turns out that this operator is self-adjoint. It has a spectrum. I put it minus lambda 1, minus lambda 2, minus lambda 3, and so on, with the property that lambda 1 is just 0, it is strictly less than lambda 2, less or equal than lambda 3, and so on, and lambda k tends to infinity. Now, when I write that lambda 2 equals to lambda 3, this means that the multiplicity, or this is the generate eigenvalue. That means that the corresponding space of eigenfunctions has dimension more than 1. You have dimensions, say, 2. I write twice, 3, I write 3 times, and so on and so forth. So once again, so one object associated with Laplace-Beltrami is, for example, Neumann, not necessarily Neumann, maybe Dirichlet, third order type, Laplace-Beltrami operator defined on this space, and it has a discrete spectrum going to infinity, and the corresponding eigenfunctions form a normalized, autonormalized set. So the corresponding eigenfunction is lambda I, and then phi I satisfies delta ng phi I equals to minus lambda I phi I. And we always assume that phi I by phi j in this L2 with measure d mu g equals to delta ij. So this is autonormalized system that makes us a basis of Fourier expansion, and any function has the form f of x is the sum fk phi fj of x, with fj usual Fourier expansion. And this, of course, is just the integral over omega of f of x phi j of x d mu j. Okay, so we can expand any L2 function in this Fourier series using the eigenfunctions of the Neumann operator. And by the way, phi 1 will be just 1. So since we make volume element to be probabilistic, phi 1 is just constant function equal to 1. That is the first object. The second object that is associated with this Laplace-Beltrami and actually closely associated with Neumann operator is heat equation. So we are looking for the following function. Right? And we assume that, let me call this normal derivative to be denoted by d nu u. So d nu u on the boundary is 0. And I assume that f is 0 for t less than 0. And here I can assume that u f for t less than 0 is 0. So that's a heat equation. That is heat source, say sun, and we are in Madrid, so it is 36 degrees. And then UF will be the temperature. Typically, the most interesting case actually is the case when this function f of xt is a delta source. Then the corresponding solution will be what's called heat kernel. So if I put f of xt to be delta function with respect to x in y, delta of t, and again we saw it in the previous lectures, and then the corresponding solution is the Green's function for this equation, but for this particular equation it's usually called heat kernel. So then we get to the heat kernel. Heat kernel. And again, as you saw, though you have seen it for the wave equation, heat equation is useful because knowing heat equation, we can find UF for any f. Then UF of xt will be integral from 0 to t, integral over omega, h of x, y, t minus t prime, f of y, t prime, d mu y, dt prime. So, as usual, Green's function gives you the full information about solution of the direct problem. What is easy to check is that to some extent these two problems are very much related because the heat kernel and these eigenpairs lambda j phi j are very much related. Namely, you have the following formula that h of x y t is the sum e to the power minus lambda j t phi j of x phi j of y. Okay, and this for t more than 0. For t less than 0, this is 0. That's this condition. So you see from this formula, by the way, it has conversion for any positive t. You see from this formula that if you know, say, you know lambda j phi j, then you can go to h of x y t, and vice versa. You can easily understand that if you know h of x, y, and t, say for all x, y, and t, you can go back to lambda j phi j. So therefore, well, the third thing that we can put number 3 is a wave equation. And actually there is a relation between the spectral data lambda j phi j and the Green's function of the wave equation, but I don't go to these details now. But anyway, looking for the fact that 1 and 2 are similar, actually equivalent, we can always choose what is our data, either h of x, y, t or lambda j phi j, and I will typically speak about the fact that we have knowledge of h of x, y, t. Okay? So what do we need that we have knowledge of x, y, and t? Well, the inverse problem that associated with this formulation, when I speak about h of x, y, t, may be the following one. I will formulate it in the way that I will mainly speak about in this talk, and then go to some problem generalization. Assume that you are living on some portion d of this omega. Say you're living in this room, and omega is universe. So assume that you know, so d is a relative compact, well, I put a d cross is compact in omega, actually just in omega. And you know h of x, y, and t for x and y running in d and positive t. So what does it mean? It means that everywhere in this room we produce at every point a point source of heat, and we measure temperature in all other points. Then let's call it. It's called Gelfand inverse problem with local data. The question is, does this data, so you have d and h of x, y, t, and the question is, can you go from here, from this data, to omega and the metric g on omega? Can you recover? So you're living in this room and you want to recover the structure of omega. Maybe there are some holes here, right? You don't know. And the metric tensor g on omega. The other version of this problem will be the following. So it is Gelfand problem with boundary data. In this case, you are sitting on the portion of the boundary, say here. Right? You're sitting on the portion of the boundary, and the question will be, you have gamma, and you have h of x, y, t, when x and y runs over gamma. And you want to recover the same. Can you find from here omega and g? Well, it seems to be quite a reasonable inverse problem, but it is not. And the reason for that is exactly that lies in the fact that it is anisotropic. So if my metric will be isotropic, then, as we heard from the talks of Günther, this problem will have unique solution. But since the problem is anisotropic, you don't have unique solution. And the reason is quite simple. So okay, so let me have this domain omega and its subdomain d. Once again, we're mainly speaking about the local data, though the quite big number of results may be extended for the boundary data. You have this domain d in a larger domain omega, and then you do what is called change of variables. So you go from the variables x that runs in omega to the variable x tilde, that is x capital of x, and this runs in principle in some other region, omega tilde. So something like that. By the change of variables, say go from x to everywhere in 2x except for with one more condition. This if x lies in D, then x capital of x, that is x tilde, is just x. So you don't touch the domain where you make measurements, but otherwise you change coordinates, and therefore your domain may change, may or may not change to omega tilde, and you introduce on this new domain omega tilde new metric tensor g tilde ij of x tilde. This is g kl of x dxk over dx tilde I dxl over dx tilde j, and the point x here actually is x minus 1 of x tilde. Okay. So this is the thing that you get used as sort of Jacobian change. So that's a new metric that you introduce at omega tilde. And now assume that you have the function, this heat kernel h of x, y, t in the original domain omega, and look at the following function. H tilde of x tilde y tilde t, that is h of x, y, t, when x tilde is x capital of x, and y tilde is x capital of y. You do nothing, you just look at the same function. So if the point x goes to the point x tilde, and the point y goes to the point y tilde, then you say, well, that this function h tilde of in these 2 points equal to the function h in the original points x and y. And then this is just chain rule. You can easily show that this function h tilde is a hit kernel for the Laplacian, for the Laplace-Beltrami operator on omega tilde with the metric tensor g tilde. So we have that dt minus delta g tilde of this h hat is delta y tilde of x tilde, delta of t, and normal derivatives of the boundary is 0, and of course it's 0 for t less than 0. Okay? But now look, we have this condition that when we are sitting in D, then x goes to x tilde. Basically, x stays in its place. So x of x is just identity. Therefore, you will have that these 2 functions are the same when x and y lies in D. So if some terrorist will change our world by making this change of coordinates, but he will not dare to get to this room, then sitting in this room, we will not be able to understand that he did it. Okay? So this is an intrinsic abstraction to the uniqueness of inverse problem in anisotropic case that we always need to take into account. And we see that this abstraction is due to the fact that we can make change of variables. And there is a typical mathematical method how to get rid of the arbitrariness of choice of coordinates. Or in other words, how to describe objects modulus change of coordinates. And this is the way just to look at our object as a manifold, in this case Riemannian manifold. So this is the reason that when you deal with anisotropic inverse problem, it's somehow easier to treat them as inverse problems on the, or direct problems or inverse problems on the Riemannian manifold. So now I want to make a change of the attitude and go to the manifolds. And now, well, manifolds actually, especially if you look at how Riemann defined them, it's nothing very, very complicated. Well, we know that we are living on the surface of the Earth that is a surface, a 2-dimensional surface, right? You know what is, you can imagine a lot of 2-dimensional surfaces in R3, sphere, ellipsoid, the surface of torus. You can imagine also curves in 3-dimensional space. And in general, manifold, Riemann manifold, can always maybe represented as some, say, m-dimensional manifold will be represented as m-dimensional surface in high-dimensional space Rn. That means, well, when you want to measure, say, the distance on the surface of the Earth, this distance comes from the distance in R3. You have a Euclidean distance R3, and the distance along the surface is just you restrict your distance in R3 to the surface. And that's the same with manifolds. So if you have an m-dimensional manifold, you can always find n, large space n, so that your manifold will be m-dimensional surface in this Rn. Let me try to draw what we have. Well, I'm not really good in drawing m-dimensional objects in n-dimensional space when n, say, is more than 4 or even 3. But let me do it for the surface. So locally, any m-dimensional surface in n-dimensional space is defined as following. You have the functions psi1 of x1 xm up to psi m in psi n of x1 xm, and say our x's belong to some, it may be ball or whichever in Rm. And so what you have here, this psi of x is a map from UU onto Rm. So x is m-dimensional, but the point is in Rn. So let me try to draw it. So for example, well, this is our two-dimensional case. So we have here U, and that's the portion of the surface, three-dimensional surface of 8. So this is U1. It's two-dimensional, and this is two-dimensional surface lying in R3, and that's only part. Then you need, so it's a piece, you cut a piece of surface. Then you need to glue them when they come together. For example, there's another U2, and the piece of surface will be like that. Yes, so this is the portion of the surface corresponding to U2, and then you glue them when they intersect. You glue them in a smooth way, and as a result you get a large surface, the real surface. So that will be an m-dimensional manifold, Riemannian manifold, if we also assume the distance along here in between 2 points, say this one and this one, is just more or less, when they're close, is the usual Euclidean distance in Rn. So when these 2 points, say I put P and Q, are close, then the distance on this surface, m-dimensional surface, is actually the distance in Rn, Euclidean distance in Rn. So the point is that according to Nash's theorem, any manifold can have this structure. Then, if you do it like that, you can write down this distance using local coordinates x1, xm. Okay, so when you represent a piece of your manifold in this form, you can write down the small length element between when P and Q are close in terms of dx1, dxm, and you come actually exactly to this. So to this formula. Sorry, I need to restore it. So, but now this formula is valid only on the portion of the surface where you can use coordinates x1, xm. If you go to the other portion, like here, you need to use other coordinates, x1 tilde, xn tilde, so it will be the same, but it will be with tilde. Okay, so if you use some other coordinates, the metric tensor G ij will change its form. It becomes G tilde ij, and you will have this relation between these two metric tensors. Okay? So that's the way how to define metric invariantly, independently on the way which coordinates you use. And that's the differential manifold. You somehow use whichever coordinates you want and don't bother about them. Okay, so so let me further decrease our problem again for the question of simplification. Assume that now, since we are working on the manifold, say surfaces in R3 or three-dimensional surfaces in R25, assume that our manifolds have no boundary, like our Earth, the surface of the Earth. So these are closed manifolds. I wanted just to forget about boundary condition. Then you have Laplace operator on the manifold. And Laplace operator, where is my Laplace operator? Here's my Laplace operator. It has still the same form. The only point, you need to use local coordinates. Okay, so you choose some point P. Around this P you have local coordinates. You take the function f, write it down in these coordinates, and that will be Laplacian. And because of this condition, this transformation condition, it's just chain rule. You will find out that it really doesn't matter which coordinates near a point you use. The result will be the same. Okay? So it's in Laplace operator. Well, for some reason, people now speak about Laplace rather than Laplace determinant. Does depend upon the coordinates. It's intrinsic thing related to the Riemannian structure of the manifold. Now, so what will be then the inverse problem? Now assume that we are, as in old days, you have some domain D on our manifold, and manifold is probably something like that. Maybe with some holes. We don't know really. We're just sitting in this room. You have your certain domain D, and like boys, you're making all these toy games with fire. You switch on fire in this point and measure temperature in different points, then you go to different points. So you have this function h of x, y, t. And t more than 0. That's your knowledge. And you want now to reconstruct the manifold M. So I will not use the omega but M, because now it's a manifold. So you want to reconstruct the manifold M and the metric G. So we have M, and the boundary of M is empty set. So it is a closed manifold. There's always a problem. What do you need to reconstruct the manifold? Well, you probably you're mainly analyst, so you know that, for example, when you speak about L2 function, you say that any two functions that differ on measure 0 are effectively the same L2 function, correct? So in the case of Riemannian manifold, two Riemannian manifolds are the same if they're isometric. So if you have two manifolds, M1 with G1 and M2 with G2, and they're isometric, that means that there is a bijective map, actually diffeomorphism, from M1 to M2. So it is bijective, it's diffeomorphism, which preserves the distance. So the distance 1 between the point x and y is the distance on 2 between the point x of x and x of y. So this is a diffeomorphism that also preserves distance. Then you speak about, then x is isometry. Then this map is isometry, and your manifolds are isometric. And like you would say that any two L2 functions that differ on measure 0, on set of measure 0, is basically the same function. In geometry, you would say that these two manifolds are basically the same manifold. These are two different representations of the same manifold. Okay? So that's what we mean. So by a reconstruction of manifold, like reconstruction of L2 function, we don't bother about things that are isometric. They all mean the same object. And then there is a result that I think a theorem, it's Kurylev, Lassos, and myself, and this is, I think, is 01, which says that if you have this data, so if you have h of x, y, t, when x, y runs on some open set on unknown manifold, and t more than 0, then this defines you mg uniquely. And the word uniquely, once again, means that if you say, oh, I have found some other manifold than yours, then it turns out that your manifold will be isometric to mine. That means unique. And the next question is the question of stability. I don't have much time for that, but let me a little bit describe. Well, that's, of course, uniqueness is fine, but if you go to, especially to Samu's talks, you understand that we need some stability, otherwise small errors will destroy our picture completely. Is there any sort of stability in this problem? Well, first of all, what does mean stability? What do you mean that you recover manifold stably? How you compare these manifolds? If you go to our picture of omega, you would say, well, at least in this case, we can know what is that because we have omega, so, and we have g's there in this omega. So that means that we, from this data, we recover omega more or less, and g more or less. But it's not the case. That's the picture. You have the change of coordinates, and the omega tilde doesn't look like omega at all. And moreover, even if omega tilde is omega, your g tilde may be as far from g as you want. So we should have another notion what does it mean that two manifolds are closed? And where comes this definition. Now, this is this goes to the theory of Gromov of comparing actually metric spaces, not necessarily even manifolds, compact metric spaces, and it's very sort of weak notion. I mean, later when you can prove that you have stability with respect to this notion of closedness, you can try to improve it. But the first thing is even to check with this one. So what is the notion, Gromov notion of distance? So assume that we have two metric spaces. So we have metric space, I put it, oh no, I used M. Okay, I put X, though X is usually, so it's metric spaces X with distance D, and metric space X tilde with distance D tilde. These are compact metric spaces. Now assume that on each of these metric spaces, you give me epsilon, some positive number. And assume that on each of these metric spaces, we have an epsilon net. So epsilon net is a finite set of points x1, xl of epsilon, and this is little I is in x, and similar object x1 tilde, x tilde l epsilon, and there should be the same number of points. If it's not the same, you probably need to count some points twice, say x1, x1 twice. And this is in x tilde. And their epsilon nets, so epsilon net, means just the following, that if I write about that. If you take the union of balls of radius epsilon centered in all points xi, okay, that will be the whole x. If you take balls of given radius epsilon with center in xi, and then you take their union that covers the whole x. In other words, this means that for any point x, so let me try to draw the picture. So that's our, say, x, and we have many, many points like that. So if you have balls, they cover the whole x. So for any point, there is at least one nearest point from this xi with a distance less than epsilon. What does it tell you? It tells you basically that you know, if you know distances between xi and xj, you know approximately the distance between any two points on the manifold. Because if you take point x, it will be close, epsilon close to some point xi. You take the other point y, it will be close to xj, and then the distance between x and y will be approximately the distance between xi and xj, correct? So that's a finite approximation of the metric space. So that is something that I think someone who is not here, he's there, should like. Because it's finite approximation of continuous object. So once again, we return back to the definition of Gromov distance. So for a given epsilon, there are epsilon nets here and here with the following property. You look for the distance between xi and xj and compare it with the distance between xi tilde and xj tilde. And this is less than epsilon. And then the Gromov-Hausdorff distance between x and x tilde will be actually infimum of all epsilon more than 0 that satisfy those properties. So it will be infimum of all possible epsilon. So there are epsilon nets which distort distance not more than by epsilon. Okay. So that gives us the weakest way to compare any metric spaces, in particular compact Riemannian manifolds, because on them we can measure distance. So any Riemannian manifold is simultaneously metric space, and we can try to compare them using this definition. We want to have continuity. That means we want to say that if our data h tilde of x, y, and t and h of x, y, and t are closed when x and y belongs to D. So we have h tilde corresponding to some manifold m tilde and h corresponding to manifold m, and we measure on D these h's and they're closed. Then this manifold are closed in the weakest possible sense, in the sense of Gromov-Hausdorff distance. Is it the case? Well, of course, we need to introduce the notion of closedness of heat kernels. Oh, well, it turns out later, we of course can produce a lot of functional spaces definitions, but what we know that h of x, y, and t is continuous with respect to all three parameters, x, y, and t. So it's very natural to use norm of continuous functions. The only point we need to take care that when t goes to 0 and x equals to y, I would not recommend you to put your finger at this point, because h of x xt goes to infinity when t goes to 0, right? So therefore, a possible, it's not necessarily the unique one, definition of the topology on the space of measured data, this means h of x, y, t will be the following. So we consider it as the space C, D, D cross 0 infinity. So this is a locally convex space. It's not a norm space. Then the norms will be the following. So you take you take a sequence of norm. So it is the function, and you have the norm in C, D, D cross AB. So you vary this interval AB, and AB is an interval in 0 infinity. So you don't go to 0. A is not 0 because it belongs here, right? So we increase A to 0 and B to infinity, you become stronger and stronger norm, but the result is will be locally convex space, not or in other words, Frechet space. So that's how you can compare. It's a very natural thing. You just compare temperatures, the values of temperature. So the question: assume that we know that these two objects are, say, epsilon delta close with respect to this norm. Let me give you a definition of delta closeness. We would say that h tilde and h are delta close if the following is true. We would say that these two measurements of temperature are delta close if for any x and y and t more than delta and less than delta minus 1. So we see when delta goes to 0, we try to cover the whole 0 infinity interval. We have this inequality. This is less than delta. So our hope is that you give me any epsilon, say 1/10, and I say, okay, if the corresponding heat kernel is less than 1 over 25 million, then the Gromov-Hausdorff distance between these two manifolds is less than 1/10. Can we hope it? No. Inverse problems are ill-posed. Let's see what this means in this case. Well, let's look for this following example. So let me take a sphere, a two-dimensional sphere. It's almost like our Earth. And then I do the following trick. I make a small hole near the northern pole. There are not many people there, so I can do it hiddenly. And then I add this tiny tube to this, and then at the end of the tube I put something whichever I want. And we are living here. We are like this penguins. We are living near the southern pole. This is our D. So this is M2 or M tilde, and M is just our usual Earth. And then you give me this delta, and I make this hole so small that for any given delta, this guy will be less than delta. And still, obviously, these two remaining manifolds, even the Gromov-Hausdorff sense, can be as large as we want. We just need to increase this neck. Well, to understand that heat kernels are close, just imagine that heat kernel, it's the probability of the Brownian motion starting at point y by the point, it's probability density, by the time t goes to the point y. And the Brownian motion, because it's so narrow, has very long, small probability to get into this neck. It will basically miss the neck during time t. That is one possibility. The other possibility is the following. Since anyway, I do the following trick. I take the same, and now I make quite a wide hole near the North Pole, but then I put a long cylinder, a pretty long cylinder in one case, and the other case, and again we make measurements here. I not only make this long cylinder, but I put something at the end of this cylinder. And again, you give me delta, and I make this neck so long that probability of the Brownian particle to get in here, to get to the end of this neck, is negligible, less than delta. So you see, and again, the Gromov-Hausdorff distance will be pretty large. Actually, whichever large you want, I can put here whichever you want. So as you know, we need to stabilize problem in this case. When inverse problems need to be stabilized, we need to put some extra condition to our data to expect that we have stability. Let us try to understand what condition can be here. And remember, our condition should be coordinate invariant. It's not something that Gij is less than 25. No, because it's not invariant. I make it change Gij and it fails. So if you look at this particular case, you remember it should be smooth, so I should do it something like that. Yes? It should go from the sphere to this tube, and should do it pretty fast, otherwise because it's narrow. And that means that the curvature is very large. So here, curvature is large. Okay. Here is everything fine with curvature because it's bounded, right? But in this case, what happens? Diameter becomes large. So we see that if we don't take care about curvature and diameter, then we can't expect stability. And the natural question, probably if we restrict curvature and diameter, there will be some stability. That means if this is small, and we know that both H and H tilde correspond to the heat kernel on the manifolds with bounded a priori diameter and curvature, this will mean that they are close in the Gromov-Hausdorff sense. And to some sense, hopefully this is true, but now the result is slightly weaker. But instead of going to the result, I try to explain you how these sort of results are obtained and what is actually the theoretical background of Tikhonov method. Because that's what is Tikhonov method, really. Well, the theoretical background of Tikhonov method is the following small lemma from topology. So if you have this as a compact Hausdorff space, and any compact metric space is compact Hausdorff space, and this is the map F into some other topological space, and assume that you know that first F is bijection, and second F is injective. sorry, is continuous, sorry, is continuous. Then this will imply that f minus 1 from y to x is continuous, and you have stability. Then this will imply that the inverse map is continuous. Look what we do in inverse problems. In inverse problems, we have models. Someone will interrupt me and say I'm not right. So we have the models that we know by x. We have a direct map then into the set of data. And when we choose only the image of this direct map, we obviously have subjective map. Then what we prove, we call it uniqueness. We prove basically that this direct map is injective. And well, by this or that work, you can prove it's continuous. So the only then you can expect that if you can prove that x is compact, that's the only thing that's important, then inverse map is continuous. Okay, so looking at this picture, we want to construct, by putting restrictions on the curvature and diameter, a compact set of Riemannian manifolds. Riemannian manifolds lies in the metric space with respect to Gromov-Hausdorff distance. So we can speak about matrix compact set there. Then for each this Riemannian manifold, we construct this h of x y t. We can compare them. We should prove that this h of x y t is continuous. So let's write our program. Actually, it will be your program to a large extent. Not much is known in this direction. So, so we have the space of manifolds with the condition that curvature is bounded. I don't write which curvature, it's not really important in this case. Okay. Then you have the map heat kernel. This is heat kernel to h of x, y, t, when x and y runs on some chosen domain where you make measurements. And in here you have this topology of C, D, cross 0, infinity. And what you need to do to apply this generalized Tikhonov result, you need to prove that this M of lambda is compact and this map is continuous. Okay? It is some analysis to prove that it's continuous, but you can do it. And it seems that we've done everything, because there was this result of Kachalov, Lassus, and myself, that if you have this information about heat, if heat kernel is given, then you recover M uniquely. So everything boils down to the proof that M of lambda is compact with respect to Gromov-Hausdorff convergence. And it turns out that is almost the case. Namely, it's sort of the basic theory, well, it depends on which curvature you're speaking about, but if it is sectional curvature, that is the principal result of Gromov, who claims, if you also say that the dimension of M is, say, equal to M small, because he put it for arbitrary dimension. So if you put this condition, you look for manifolds of dimension M with bounded curvature, with bounded diameter, then so this is the result of Gromov of 81. It's relatively compact. It will become compact when you close it in the Gromov-Hausdorff sense. Do you have 5 minutes? So we need to close these objects in the Gromov-Hausdorff sense. Then we get compact, but then we need to restart everything again, because we need to prove that now we have uniqueness of inverse problem on this larger class of objects. You need to prove that you have continuity on this larger class of objects, and then you can prove that inverse problem is continuous on this closure, and therefore is continuous before closure. And the issue is to analyze this generalized object that obtain as a limit. So we need to look for this closure and see what lies there. And the problem for us as analysts is that objects that lie there may be pretty nasty. They have metric and measure separately, metric measures. Therefore, you can speak about generalization of Laplace spectrometry operator and about heat equation. But they're still pretty nasty, and therefore, at the moment, what we can do is only for some special case. Special case is when, what can happen here? Well, it's actually quite simple what can happen here. It's not something enormously difficult if I find how to show it. Let's assume that you deal with a torus. Assume that you deal with a torus. Torus, by the way, usual torus, Euclidean torus, has curvature 0, so everything is bounded. And then you do the following trick. One trick. You make this radius, perpendicular radius, go into 0. And as a result, you come to just a circle. From two-dimensional object, you come to one-dimensional object. Or you can make both radii go into 0, and then it goes to the point. You shrink it to the point, and it's everything fine. Curvature is bounded, diameter is bounded. So what can happen when you close? You can lose dimension. It's called in geometry collapse. And by losing dimension, you simultaneously, that's a nice picture because everything is smooth, the things become singular. And to understand the singularities, ladies and gentlemen, you need to work hard, but I hope you will work to find what's in general case. What we did, it turns out that when you lose at most one dimension, the object that I wanted to speak, and Matti gave me pictures, but I probably don't have time, that obtained as a result is not much worse than manifold. It's orbifold. It's the next generalization from the manifold. And for orbifolds, we can prove uniqueness of inverse problem. Okay, so, but we need to be sure that we can't lose more than one dimension. And to do that, we add one more condition that is also geometrical. So we look for the following class of manifolds. They're parameterized by one more parameter. In addition to lambda, you know what is lambda? It's some c. C is more than 0. With the following property, that if you look for this probabilistic volume of the ball of radius r, with a center at any particular point x0, it will be less than cr to the power n minus 1 when r is less than c minus 1. So that's a restriction how the volumes of these manifolds decay when r goes to 0. So if you put in addition this condition, of course you decrease your space of possible manifolds. Then its closure of this space contains at worst n minus 1 dimensional orbifolds. And for this n minus dimensional orbifolds, you can basically prove the same results about uniqueness as for the manifolds. And therefore, you can apply this lemma, topological lemma, and say that your inverse problem is stable. And let me formulate 1 minute the result. Let you have two manifolds, M1 and M2. They both belong to this M lambda C. This is our a priori information. Curvature is bounded by lambda, diameter is bounded by lambda, and the volume growth is like that. Let you have two balls, say of radius 1. So 1 and 2 is not radius. Radius is 1 here. It just B1 lies in M1, B2 lies in B2. And you have then for any delta more than 0, or for any epsilon more than 0, there is this delta depending upon epsilon, and delta goes to 0 when epsilon goes to 0, so it is continuity function, modulus of continuity function, such that if these both Bn1, Bn2 have a delta network, sorry, epsilon network, so x1, 1, xn, 1, and the same is 2, I put it I here. This is epsilon net in Bi. So we are living in Bi, and there is this epsilon nets in Bi with the property that h of x, h1 of x1I, xj1 minus x2, x2I, x2j is less than epsilon for t, oh sorry, t here, for t between epsilon minus 1 and epsilon, sorry, epsilon and epsilon minus 1. Then we would have that Gromov-Hausdorff distance between M1 and M2 is less than delta. So they're close. Now, homeworks, just for one day, because tomorrow is the last day. The first thing is we prove this only when collapse is one-dimensional. What happens when collapse is multi-dimensional? The second thing, it's only for some other case, special case, when you have extra condition of injectivity radius bounded from below, that we come from these qualitative results. We are close to the quantitative results to find what is delta of epsilon. For other case, it's just qualitative results. So what is this delta of epsilon? And the third thing, to get these results at the moment, in the majority cases, you should work with manifolds without boundary. What happens when you have manifolds with boundary? So you have just one day. Thank you.
Questions? Anyone who wants to answer this?
No, they have one day.
Yeah, but
Don't rush people.
Okay, then let's go into a
Thank you.
coffee break. Yeah, thank you very much.